and welcome to my video. I don't know why you're here. You could be here for a variety of reasons, but we're just going to get it started. The question is, how many particles of air have you breathed that have also been breathed by a prehistoric dinosaur? So I'm going to get sheet 1 out of 3 down right here, and we're going to get going. So I'm going to start with a few assumptions that I have, a few things you need to know before we really get deep into whatever this is. Molecules of air in the atmosphere is 10 to the 44. This is quite accurate. People have measured this and people have calculated this a fair number of times. So this actually has a quite good level of accuracy to it. But the next assumption doesn't really have that those same characteristics. The amount of dinosaurs that ever existed, I'm saying, is about 10 to the 16. If you ask a paleontologist this question, they'll be too scared to lose their job to tell you. But I got this number by assuming about 75 million square kilometers of inhabitable landmass throughout the 186 million year period where the prehistoric dinosaurs flourished before the asteroid came down and washed them all away. And I'm like, okay, 1 dinosaur per square kilometer is a little too low. 100 dinosaurs per square kilometer, that seems a little bit too high. We're just going to Goldilocks method it. Go for 10 dinosaurs per square kilometer, and I'm going to assume a 20-year turnover for these dinosaur populations. So that's our number, and that's how we got it. This definitely has, or probably has the most deviance out of all the numbers that we're going to be using in this measurement. The average weight of a dinosaur, where you're probably thinking why we need the average weight of a dinosaur, but we'll get to that. We'll get to that. Is 1,000 pounds. This is sticking to our theme of numbers with 10 and an exponent, although I decided to just write this one out. And that is what we will be assuming in this problem. Our atmospheric density at the dinosaur's existence was 30% oxygen and 70% nitrogen, hydrogen, trace elements, whatever. The reason we need to know this is because the atmospheric density now is different than the atmospheric density then. So what this allows us to do is it allows us to find the oxygen usage of a dinosaur and then correlate that to the amount of molecules of air that a dinosaur would use. And then it allows us to correlate that to our current atmosphere. So that's why we need this. I thought I'd need my breathing rate. It's 20 breaths per minute. My very fancy $99 watch tells me exactly what my breathing rate is. So this is pretty accurate, but we didn't need it. So don't worry about that. My age, I had to check my driver's license and find out how old I was. Turns out I'm about 18 and a half years old as of today. I thought I'd need that. I also didn't need that. And this is an excluded volume calculation, which means that every molecule that a dinosaur breathes in, they breathe out. The next breath they take in shares none of the molecules from the breath that they just exhaled, which is a little bit generous. But it isn't crazy. These guys are moving around outside. You know, they're doing whatever dinosaurs did. They probably had a blast. You know what I mean? They're partying, you know. They got some HVAC systems going on. They're not breathing in the same air. All right. That's crazy. We're going to start this off by finding the oxygen usage of a dinosaur. Because as I mentioned here, we kind of need it to find the amount of molecules that a dinosaur would use in their breath. And to find the oxygen usage of a dinosaur, I first found my oxygen usage, and then I just scaled it up to a dinosaur's oxygen use. We're both multicellular organisms that use oxygen for fuel, so I didn't think it'd be too inaccurate. I'm going to preface this by explaining what a VO2 max is. You could probably skip about 20 seconds ahead if you already know what this is. But a VO2 max is the maximal amount of oxygen that your body can use per kilogram of your body weight per minute of time. So if you are running or if you are sprinting, if you're doing a maximal exertion activity, you're trying your absolute hardest, you have a rate of how much oxygen your body can utilize per kilogram of your body weight per minute for ATP synthesis or to create energy. I multiplied my VO2 max. My VO2 max is 50 milliliters of oxygen per kilogram per minute. I multiplied this by my weight in kilograms. I weigh 165 pounds, and that's about 74.91 kilograms. Multiplied this out, canceled out the kilograms, and I found that at maximal effort, I can use 3,745.5 milliliters of O2 per minute. But I want to find the average amount of oxygen I can use. I don't want to know the maximum amount of oxygen I could use, because these dinosaurs aren't sprinting around all day. You know, they need to have some chill time too. So I decided to add my maximal exertion to my minimal exertion and divide that by 2. And the minimal exertion just happens to be your maximal exertion multiplied by about 17.5%. So I multiplied this out and I found that my body's average oxygen use throughout my lifespan is 1,545 milliliters of O2 per minute. Now moving on, knowing this number, I'm going to correspond this back to my mass, which is 165 pounds, and I find that per pound of my body weight, I use 9.36 milliliters of oxygen per minute. And then we correlate this to a 1,000 pound dinosaur, and we get that a 1,000 pound dinosaur will use 9,363.5 milliliters of O2 per minute per dinosaur. The units start to get a little bit funny here. We take our 9,365.5 milliliters of O2 per minute per dinosaur. We multiply it by our 10 to the 16 dinosaurs that we talked about earlier. The dinosaurs cancel out. And we get 9.3635 times 10 to the 19 milliliters of O2 per minute of oxygen that all of these dinosaurs coexisting at once would use. But we're looking for molecules. We're not looking for milliliters. So I convert our milliliters to molecules by multiplying it by the conversion factor of molecules of O2 per milliliter of O2. And it comes out to 2.52 times 10 to the 39 molecules of O2 all dinosaurs existing at once would use per minute time. I'm going to abbreviate this as this once because I didn't want to write it out again. We know this number, and because this is the amount of oxygen that all the dinosaurs coexisting at once would use per minute, I multiply this by the amount of minutes in our average lifespan. And we find that the molecules of O2 consumed by all prehistoric dinosaurs ever is about 2.65 times 10 to the 46. That ever was hilarious. But the question is particles, not just O2 particles. And knowing that atmospheric density was 30% oxygen, we must multiply by 3 1/3 to find the whole amount of particles, because 30% times 3 1/3 is 100%. We do the multiplication out, and we find that the total amount of molecules of air breathed by all dinosaurs is 8.8 times 10 to the 46, which is significantly higher than our number from earlier. With our molecules of air in the atmosphere number, it is significantly higher. So that means the question isn't how many particles or how many molecules of air have you breathed that have also been breathed by a dinosaur. It's how many times has each particle that you breathe passed through a dinosaur's lung. And if we divide it out, we find that every particle that you breathe on average has passed through a dinosaur lung 883 times, if we are assuming just a complete mix of the atmosphere, which most definitely can be assumed because they were so long ago. Which is quite strange, you know. Every you breathe in, you're a part of history to an extent, and I assume that this has the same effects with the water that we drink. I'm sure the water that we drink has been peed out by some dinosaur thousands and thousands of times. So this is the conclusion of this video. I have nothing more to say. I don't have anything of extreme moral value, but remember where you came from, I guess.